Hello everyone. Welcome to the Model-Based Systems Engineering webinar, SysML Made Simple with Magic Grid Framework. During the webinar, we will cover the following topics. Where does CATIA Magic fits in the overall systems engineering lifecycle? The value of standards, OMG Systems Modeling Language, SysML, Magic Grid method, live demonstration session, and questions answers time. For your information, questions in the written form can be provided during the whole session. You can type them in the questions pane on the webinar panel. Today's session is held by two of us. My name is Aiste Aleksandravičienė, CATIA Magic Cyber Systems Industry Business Consultant. I have bachelor and master degrees in information systems engineering and 16 years of experience in software and systems engineering. I am a member of INCOSE, the author of the Magic Grid book, and a member of the Magic Grid development team. I will do the live demo session for you later on, and now I am giving the word to my colleague to introduce himself and to cover the first three topics of our today's webinar.
Hello everyone, my name is Aurelijus Markevičius. I'm the manager for a team of consultants for CATIA Magic Solutions for the EMEA region. I have PhD, master's and bachelor degrees in software systems engineering, have 15 years of experience in software and systems engineering, working with different customers worldwide. I'm involved in the standards development. I'm currently co-chairing a unified architecture framework in the object management group. I'm also the member of International Council of Systems Engineering and NATO Architecture Capability Team. Also, I'm an author of Magic Grid method that will be presented in this webinar and co-author of Magic Grid Book of Knowledge together with Aiste. First of all, I would like to introduce you to the objectives of this webinar. Our objective is to demonstrate what are the three core elements to establish a successful model-based systems engineering solution and model-based systems engineering culture within an organization. It is language, method, and tool, and that only using all three in combination, successful results can be achieved. We also want to show how easy systems modeling language, one of the elephants, can be if applying it together with the proper tool and the method. We will start from where does CATIA Magic fits in the overall systems engineering lifecycle. And why this topic is because model-based systems engineering is understood and applied differently by different communities. However, there are some fundamental principles and practices that are common to all, and they are described in INCOSE handbook and ISO 15288 standard. So this section is to highlight key systems engineering concepts and their definitions. Also MBSE in the context of digital engineering transformation. And the goal of this is to provide you the better context to understand which processes in the systems engineering lifecycle we will cover further in the webinar. So first of all, the difference between systems architecture and systems design. When we talk about systems architecture, we talk about more abstract, concept-oriented, global, focus to achieve the mission, high-level structure in systems and system elements. And when we talk about design, it's more technology-oriented. We are talking about physical, structural, environmental, and operational properties constraining implementation or forcing decisions for implementation and really focusing on compatibility with technologies. And this is really different from what we do in the architecture. And if we look into a systems engineering lifecycle, the foundation for it is the INCOSE Systems Engineering Handbook and also ISO 15288 standard. It describes major processes in the systems engineering, where we start from business mission analysis, then we go to stakeholder needs and requirements, then we transform those stakeholder needs into system requirements. When we have system requirements, we start defining the architecture. Then we go to the high-level design, which is still logical and technology independent. And from here we go to detailed design, then implementation, integration, testing, and sustainment. So these are the core processes, and in the scope of this webinar, we will talk about the scope that falls under the conceptual to logical system architectures. We will not talk about physical system architecture. So we will cover a little bit of business mission analysis. We will talk about stakeholder needs. So these two are really inputs for system architecture and system requirements definition. And then we also go to the high level design. This is the point where transition goes to the detailed design, and this is where the different tools in the 3ds portfolio can be applied. Next, we will talk about the value of standards, and especially OMG systems modeling language. So you all probably know the story about the Tower of Babel. And you know that only speaking the same language, you can build tower as high as to reach the sky. So the common language, it enhances communication between engineers. It enables them to understand each other unambiguously. It also helps you to find new talents as the standard languages are taught in the universities. The language in general is really foundation for building architectural descriptions. It defines types and relationships that are used in the language and how relationships can connect those types. So this is really foundation for building architectural descriptions. And the systems modeling language is the graphical modeling language for specification, analysis, design, verification, and validation of systems. It was created in 2006. It's dedicated for modeling complex systems, whatever falls under the definition of system. It can be modeled using systems modeling language. It's supported in multiple tools, it's interoperable, and according to INCOSE, it is a critical enabler for model-based systems engineering. The language consists of 9 types of diagrams and also categorized into 4 pillars. If you look in what the pillars are, they are structure, behavior, requirements, and parametrics. Let's look into some of the diagrams. Internal block diagram, state chart to define the life cycle of the block, requirements, in this case captured in the tabular view, that's also the part of the standard, and parametrics, which is used for mathematical calculations. So breaking the myth, SysML is too complex. There are many people saying that SysML is too complex for their daily engineering activities. But first of all, we need to understand a couple of things. First of all, SysML is the modeling language only, so it needs to be combined with the methodology to be useful. The other thing is that no open source tool can provide usability equal to commercial SysML tools. So if you apply open source tools, you don't really have the experience of the commercial SysML tool and how easy it is to build models in one of the commercial tools. The SysML is a formal language, so we have to understand that it's not comparable to PowerPoint and Visio. So if we want to keep some level of formality, we need a little bit of complexity. But again, it depends on how precise models we want to build at the end. It can be very precise, it can be less precise. It really depends on which level of the systems engineering lifecycle we are at. And SysML has strengths that no other languages have. For example, contextualization. So the systems can behave and be connected differently in different contexts. Just imagine taking your laptop, bringing into auditorium and connecting it to the projector using HDMI. And imagine next day coming back home and connecting it via some protocol to your TV. It would be different use of the same system. So that is really powerful concept. Then instantiation, so the systems can be deployed with unique characteristics at different point in time. So we can have systems with different characteristics dependent again on the time, see how they changed, deploy different characteristics in different missions. Of course, we can simulate systems, and more importantly, we can simulate them using standards, like, for example, FUML from the object management group. And it's important to understand that as SysML is formal, you don't necessarily need to generate code to be able to execute the model. Finally, it's easy extendable if there is necessity for that. So it means that you can really adjust the language to the language you have in the organization if there's need for that. Of course, you always need to understand that extensions need to be maintained. So that is additional money. But if it is necessary in your organization, that's definitely the way to go. And again, I want to get back to the first point. The modeling language is just the language. It must be combined with the methodology to be useful. So that is our next topic for today. As we described the language already, now we're going to go and describe the method. We're going to talk about Magic Grid from Dassault System. It's called grid because it's represented in a grid where we have columns and rows. The rows are layers of abstraction. We also call them domains. And the columns are pillars. So we already introduced pillars when I introduced the SysML language. So their requirements, behavior, structure, and parameters. Now, if we look into domains, first of all, we have problem. A problem is to describe the problem that we are trying to solve with the system that we are going to design. Then we have solution. This is where we offer one or couple of different solutions to solve the problem. And finally, we have implementation, which talks about component design, which talks about software components, electrical components, mechanical components, fluidics that are needed for the system. So this already falls to the different engineering practices and different tools. It is here in the grid just to show the integration and the continuous life cycle of the systems engineering. So first of all, looking into the problem, this is where we have black box and white box. In the black box, we define the system from the black box perspective. In the white box, we define a system already going inside and seeing what are the main processes, what are the main functions that system provides, what are the main logical components, and what are the main characteristics of those different components. Then if we go in the solution, we can have a couple of different layers here. So we definitely start from systems layer, then we can go to subsystems, then we can go to components. Or if it's complex system, it can go down from the subsystems to the subsystems of the subsystems, and so on and so forth. So we can have multiple different layers until we reach the final one component layer. And this is where the high level design ends and where the detailed design starts. And this is where we go into different engineering practices as described in the implementation domain. Also on the right, you can see specialty engineering. So this is where we talk about safety, about security, about integrated testing. And so these are different perspectives that can be added to extend the Magic Grid. But Magic Grid itself does not define the practices in specialty engineering. It just says where those practices fits. And all that is described in every cell is captured in the Magic Grid Book of Knowledge. So it's a detailed guidance that provides you detailed instructions of how to create system architecture from A to Z of the system of interest. If we look more into details on how Magic Grid maps to ISO 15288, we can see that first of all, the input to the Magic Grid is the business and mission analysis process. This is where different practices are used again. And talking about CATIA Magic Portfolio, we talk about system of system architect tool that allows to capture high-level business analysis, business processes, and business needs that later can be input into the systems engineering that we perform using Magic Grid. And first of all, we have those stakeholder needs. When they are defined, we start with the developing operational concept. It means what are the main core use cases, what are the main systems that interact with our system of interest, and what are the main KPIs, main measurement of effectiveness we have to achieve. Once we have operational concept developed, we then start working in more details on the functional architecture, on the logical architecture of the system, also identify measurements of performance, and so on and so forth. And we call all this process is really a transformation of stakeholder needs into model-based stakeholder requirements. So we take raw stakeholder needs and we try to describe them, to refine them with the model. Once we have problem defined, we go into solution domain, or this can be the boundary where we start talking to suppliers. It really depends on the situation. And this is where we can have one or several solutions proposed. And in case there are several solutions proposed, this is where we do trade-off, trying to figure out which solution is better to solve our problem. So if we look in the solution domain, first of all, we talk about system requirements. This is where we define system requirements based on the information that we have captured in the problem domain. Now, the requirements here are derived from the stakeholder needs, and also they are here coming from the model that we have created in the problem domain, talking about behavioral model, structural model, parameters. So there is a traceability between system requirements and the problem domain. Well, the system requirements are further satisfied by the architectural data. So once we have system requirements, well, actually, I should say it's ongoing process. But first of all, we have to have at least some of the system requirements to start with the system architecture. Later, of course, we can add additional system requirements once we progress with the architecture. First of all, we define the high-level architecture. Then we go to the high-level design. This is where we go into subsystems of the system, and this is where we can start looking into different subsystems, distributing the subsystems as the separate work packages to the different organizations or to the different departments within organization. This is again where we can do trade-off at every level. Then we go to detailed design for the components. Again, it can be us, it can be our suppliers. It really depends how we organize the work. And finally, it's implementation, and this is where the entire solution domain can be treated as requirements for the implementation. And this is where Magic Grid is not going further and describing practices that happens in the implementation domain. Now, if we look into those concepts of the model-based systems engineering and model-based design, we can, using Magic Grid, we can draw a clear line separating where model-based systems engineering is done and where it goes already to the model-based design. It's really important to distinguish these two concepts to make sure that we are talking about the same, that we are talking about the problem domain analysis, that we are talking about logical solution when we talk about MBSE, and that when we talk about physical design, when we talk about platform specific characteristics of the systems, we are talking about model-based design. So now looking into the grid more precisely, we will talk about the problem domain in more details. Then we will talk about solution domain in more details. And later on, there will be demonstration demonstrating of how to create system model from A to Z using Magic Grid approach. For every cell in the grid, there are recommended diagrams, SysML diagrams to be used. And you can see they're repeating because we have as I said, 9 diagrams in SysML. And it's really important to say which diagram goes where and which diagram we use for what purpose. Because otherwise you can really get lost and start using wrong diagrams for the specific need that you have. So it's important to understand which diagrams we're using for every cell in the grid. And we will, of course, cover that in this webinar. So first of all, let's talk a little bit about problem domain. We'll start from the black box. The black box analysis is really when we talk about the system as a mystery box. So we don't know yet what's inside the system. And our goal here is to understand what are the main stakeholders, how is the system going to interact with the environment. We have actors, we have users, we have influencing factors like climate, for example, for some systems, or the road for the systems like vehicle. So we have to take all that in count, and we have to define how all those external entities interact with the system. This is where we really start identifying interfaces. What are the inputs? What are the outputs? And capture also non-functional characteristics like measurements of effectiveness, key performance indicators, and so on and so forth. Basically, we do what is called and known as operational analysis. Now we will start from stakeholder needs. Well, first of all, the system of interest in the small example is vehicle climate control unit. And there are a couple of stakeholder needs for the climate control unit. It's important to know that stakeholder needs are coming from different sources. They can come from government as the regulatory requirements. They can come from the budget, from the marketing. They can come from the business as the budget requirements, and they can come from the user. So really, there are many different sources of information, and it's important for us to categorize that information to make it in a more formal approach so that we can trace to these requirements. This is what is done in the modeling tool, and what is the first step in the Magic Grid approach. Once we have that information captured and categorized, we can see it in a different format, like for example, this traceability graph. So once we have the stakeholder needs, we need to start refining them, because there are different stakeholder needs, not only because of sources, but they are also different nature. Like, for example, we can have functional stakeholder needs, we can have non-functional stakeholder needs, and this is where we need to refine them and try to figure out which stakeholder needs to be refined by the use case, or which stakeholder need needs to be refined by the interface, or the measurement of effectiveness. So this is what we do in the next steps, and we start from the system context. And the system context, we define how our system of interest interacts with the environment, how it interacts with external systems, how it interacts with users, how it interacts with external factors like climate or road condition, etc. So this is usually a nice looking diagram with a nice picture. So we can take this diagram, put it on the slide, and show it to the stakeholders, explaining the main principle of the system of interest. This is also where we start capturing for signals. We can see on the right the signals in the model, and these signals are captured in the diagram, where we can see what type of inputs and outputs we need to have in the system. And this information is further refined with the model, and also it will be presented in more details in the demonstration. Then we go to the use cases, and this is when we start looking into functional requirements, and we start identifying what are the main functions that are expected from the system. And this is where we capture what are the core user needs, functional needs from the system. Of course, we detail this information with the different use case scenarios. And in the use case scenarios, we capture how user interacts with the system, where on the system side, we are describing the core functions, the top level functions of the system. These functions can be further refined going in the white box analysis. But in the black box analysis, we only need to capture the user expectations and what are those core functions that user expects to get from the system. Finally, we go to measurements of effectiveness, and this is when we capture non-functional characteristics, non-functional measurable characteristics, I should say. And for example, like for the climate control system, we capture measurement of effectiveness as sound level, total weight, total energy consumption, etc. Later, we will define how these measurable characteristics are calculated, what are the methods to calculate them. But at this level, we only identify what are those main characteristics. Then we go into white box analysis, and this is where we open the black box, this mysterious box, to see what is inside and to start talking about the internal behavior of the system of interest. Start talking about the logical subsystems. So really we define functional architecture, we define logical architecture, and we define the interfaces between the subsystems of the system of interest. And of course, we go and refine measurements of effectiveness. So we assign different measurements of effectiveness or measurements of performance to the subsystems of the system. And this is where it's important to be consistent between behavior and structure. So we have to make sure we are talking about the same level on the behavior side and on the structure side. So if we have system use case is related to the context. So a different system context can have different use cases. The system in context can be imagined as different situation in which the system is operating. So it can be, if it's vehicle, for example, it can be in the maintenance, or it can be on the road, or it can be in the garage. And these different situations have different use cases. And then going further, we have the core level functions, and they are the functions of our system of interest in that specific context. Then we go further down, we have sub functions, we have also subsystems, and so on and so forth. Just we have to make sure we are not going into very deep details. We don't need to go to the physical components here. So we just identify what are the main functional groups, so-called logical systems. Some people call them functional blocks in our system. So this is where we start from functional analysis. We continue the use case approach, and we go deeper from the use case and take the core level functions that we identified in the black box analysis and detail them with sub-functions, with what is really going on within this sub-function. What is expected from the system? How is going to work? What happens first? What happened next? How the information goes from one sub-function to the other, and how the sub-function transforms this information from inputs to the outputs. And again, this is where we need to keep the alignment between the levels. So where we can go further down, the sub-functions then can be decomposed into more detailed functions and etc. Then on the logical subsystems communication cell, this is where we capture subsystems. We start from the interfaces, where we capture what are the core interfaces on our system. And of course, we assign signals that we identified in the system context diagram to say that this interface will be used to send this signal and this interface will be used to receive this signal. So this information is captured, and also we capture here the subsystems and how those subsystems communicate with each other. Then finally, we allocate. We allocate functions to these subsystems. As you can see now, every lane, so-called swim lane, has represents subsystem, and then the functions are allocated to that subsystem. That can also be done in the matrix format. So it's a different way to capture this allocation. Finally, the measurements of effectiveness for the subsystems. So we can assign different measurements of effectiveness for the subsystems, and of course, also define measurements of performance and how they contribute to the calculation of the measurements of effectiveness at the system level. Okay, then finally is the traceability. So really what we do in the problem domain, we refine stakeholder needs. And this is captured, this needs to be captured in the modeling environment to be able to say that the specific use case refines the specific stakeholder need. And this completes problem domain. Okay. Then we go to solution domain. Again, as I mentioned, there can be different organizations working on it. There can be different departments working on it. And this is where we can already start doing trade-off. And this is where we start um, going more precise. Okay, we're not going physical yet. So it's very important to understand we are going to create system architecture here that corresponds to the problem that we defined. So from the conceptual, we going more logical and we're providing more details. And of course, this again helps us to find the best solution for the described problem. And we will go to the system requirements here. This is where we start. And the system requirements, they are derived from the stakeholder needs. They also refine model elements in the problem domain. So we identify rationale behind every system requirement, and the system requirement, they have some characteristics like unique identifiers, and also it's really, really important, they need to be verifiable. So when we talk about stakeholder needs, they not necessarily need to be verifiable. Sometimes they are raw information, raw text, which we are working on refining it in the model. And when we come up with the system requirements, they need to be verifiable. So they need to be very precise statements. Looking into example, we can capture them in the diagram. We can capture them in the tabular form that was displayed before. We can capture in the graph that I also displayed previously, and we can capture relations to the stakeholder needs of how system requirements are derived from the stakeholder needs. And of course, we can build a nice looking traceability from the stakeholder needs to the system requirements. And we go to the system structure, and this is where we define the high-level system architecture, which can be different. It can be the same, but it can be different from the one described in the problem domain. In the problem domain, we identify what are the main functional groups, and we treat it as the requirement for the system. And now when we are trying to propose solution based on all the inputs that we have, it may correspond and it may not correspond, because some of the things may be required, additional things may be required, or maybe there's going to be less because some cannot be implemented because of the cost or some other reasons. So really we are proposing the high level architecture on the solution domain. And here, once we do that, then we start splitting our model into different models for different subsystems. This is where we come up with the work breakdown structure based on whether we are giving it to suppliers or whether we are distributing work to different departments. So there really can be multiple different situations, but it's important to understand that here we really separate different subsystems into different areas of work, into different projects um, within the organization. Also so-called work packages. Okay, and here we again create the system. We show subsystems, we show the interfaces. What are the main interfaces? Please note that we are not defining connections on this diagram. It is only to identify what are the interfaces. So every subsystem, we start looking at the black box. We know what are the inputs and we know what are the outputs, but how those inputs are transformed into outputs, that's something we have to figure out. So we have to take every subsystem and we start working on that subsystem, detailing what are the main components, what are the main functionalities within it. Here, usually at the system level, we're not defining behavior. It can be defined if we are not going further, but it doesn't make sense to define it if we are going to the subsystems, going to components. We only define behavior here for the leaf level components. So then we go to the system parameters, and at the system parameters, we define methods of how we are going to calculate different KPIs. And we do that in SysML parametric diagrams. So SysML parametric diagrams, they're providing mathematical approaches to calculate the measurement of effectiveness. Okay. And this will be explained in more details when we go to the demonstration. Then it's important to know the traceability. Traceability is very important all the time. And here we have model elements from the system architecture satisfying our system requirements. So please note that in the problem domain, we are refining stakeholder needs. Here in the solution domain, we're satisfying system requirements. That is important difference to understand. And this we can capture in the matrix form, where we can say that there's some interfaces or some system parts or components, they are satisfying system requirements. Then we can go to subsystems. The same practices are applied here. We are going into more details, starting from the structure. And here in the structure, we again applying the same practices. We go into more details for every subsystem. We identify what are the main components, and we go down until we identify what type of components they are. Are they electrical, or they're mechanical, or they're software components? And then we can again either choose some components from ones available in the market, or we can contact suppliers and ask for these components. So it really depends on the situation and on the system. Okay, then the system behavior here allows to define behavior for the subsystems. We can capture of it, for example, in the state chart. We can capture the life cycle of the subsystem. At the high level, we can, of course, add some more precise and formal algorithms. We can run simulations. So this is really where we go into more details, trying to understand the behavior of the subsystem or the behavior of components, the high-level behavior of components. And if needed, integrate with some more detailed models coming from different sources, like, for example, Modelica MATLAB, Maple, etc.
Now it's demo time. And it is also time to introduce the modeling software as the third enabler of MBSE, which goes together with already introduced language and method. Why the modeling software is so important? Because it provides the repository for storing models. Without the repository, SysML diagrams would be just separate drawings, as there was no underlying model behind them. Here you can see the CATIA Magic Cyber Systems portfolio. We have three tools for modeling, and they are on the left. The first one is Magic System of Systems Architect. It supports the Unified Architecture Framework, or just UAF standard, and is used for enterprise architecture. The next one is Magic Cyber Systems Engineer, which supports SysML standard and should be used for systems engineering. The last one is Magic Software Architect, supporting UML and used for software engineering. The one to the right is Magic Model Analyst. It is not for modeling, it is for executing the models. It supports the FUML or executable UML standard and therefore can run simulation directly in the modeling environment without any code generation, which is inevitable in other well-known modeling tools. And there is also a software that enables the collaborative modeling and model review. It is on the top right. And here you can see the legacy product portfolio known as Cameo Suite from NoMagic. All the products actually are the same, just have slightly different names. Cameo Enterprise Architecture for building enterprise architectures, Cameo Systems Modeler for systems engineering, Magic Draw for software engineering, Cameo Simulation Toolkit for executing the models, and of course the software for collaborative modeling and model review. Now let me switch to the modeling tool, Cameo Systems Modeler actually, and begin the demonstration. Now I will show you how to create the problem domain analysis model for the missile system by following the magic grid method. Due to the limited time, I must skip the cells that belong to the parameters pillar. Okay, let's look now at the model browser, which is on the left of the modeling tool window. It has already got the structure of packages that correspond to the layout of a Magic Grid framework. As you can see, there are packages for domains. There are also packages for perspectives, the black box and the white box. And of course, there are packages for cells. The stakeholder needs, the use cases, the system context, measurements of effectiveness, and so on. It's important to note that you don't need to create that structure manually. Each project that is based on one of the Magic Grid templates already has that structure predefined once it is created. Magic Grid template can be selected on the new project creation. Let me show you how to do this. I'm creating a new project, and on the left of a new project dialog, under the Systems Engineering category, I can select one of the following templates, either the Magic Grid Blank or the Magic Grid Quick Start. Stakeholder needs can be captured directly in the SysML model, or they can be imported from some external software, like for example, requirement management tools, RecAF file, or Microsoft Excel spreadsheet. Today, I'm going to show how to import stakeholder needs from the Microsoft Excel spreadsheet. For this, first of all, I need to create the requirements table right under the stakeholder needs package. Let's name it stakeholder needs for missile. Yeah, and as you can see in the new table, there are two columns, the name and the text. I'm ready to import data from the Excel. In the Excel spreadsheet, you can see that there is a plain list and all the information is organized in two columns. We also have two columns in our requirements table, so we are ready to import the data. So I'm selecting all the filled in cells, all except the header, and I press Ctrl C. Then back to the modeling tool, I'm pressing Ctrl V, and here I need to select what kind of element I want to create from the imported data. I'm selecting simple requirement. All 10 stakeholder needs are imported into my model as SysML requirements. The next thing to do is to analyze those stakeholder needs and distinguish between the functional stakeholder needs and non-functional stakeholder needs, because this is necessary for the further analysis. Functional stakeholder needs are later on refined by use cases and use case scenarios. Non-functional stakeholder needs are later on refined by measurements of effectiveness. Here I can already say that the stakeholder needs as route, target, location, security, self-guided, missile design are actually functional stakeholder needs. That's why the requirements capturing those stakeholder needs can be converted to functional requirements. Let's do this. As you can see, the icons of selected elements have been changed. And now you can identify the functional requirements with the naked eye. Now it's time to move to the next cell, but before that, we need to update the index diagram. Like this, I'm dragging the stakeholder needs for missile requirements table to the appropriate cell in order to say that I'm done with stakeholder needs. Of course, at the end of the demonstration, we will get back to it, but so far we are done. The next cell, according to the Magic Grid framework, is use cases. However, they should be grouped by system context. Therefore, we need to identify them beforehand. System context can be captured in the model as SysML block. So here under the system context package, I am creating a new block to capture the missile in mission system context. Now I should specify what is happening inside that system context. That is how the system of interest interacts with other participants of the same system context and what inputs it gets from them. For this, I need to create an internal block or IBD diagram directly under the missile in mission block. The name is okay. And here it's important to note that the frame of a diagram actually represents the boundaries of a missile in mission system context. Now let me create the system of interest. I'm selecting to create a part property because the system of interest is a part of a missile in mission system context. Missile. I'm enlarging the shape because this is the main shape of this diagram. This is the system of interest. And by analyzing the stakeholder needs, I can say that there are other participants in this system context, like launch platform, GPS satellite network, atmosphere, terrestrial target, and terrain. In order to specify what items the missile gets from other participants of a missile in mission context, first of all, we need to establish connectors between them. Let me do this. If you need to get rid of breaking points, you can do like this. Now I'm ready to specify what items are flowing into the missile. First of all, I need to create them. But instead of creating them from scratch, I am going to import them from the Microsoft Word document. Here I have a list of items. I'm selecting them. I'm pressing Ctrl C. And then in the SysML model, I'm selecting the Exchange Items package, the proper place to paste them, and press Ctrl V. And I want to create blocks from this data. Everything is imported, and now I can set the item flows on the just created connectors. The launch platform provides the mission data to the missile. The GPS satellite network provides the coordinates to the missile. The atmosphere provides weather conditions. The terrestrial target provides target data. And the terrain provides terrain information. I am almost done. Just before moving to the next cell, we can decorate that diagram with images, especially if we want to show it for the people who don't read and don't understand SysML. So the images can be taken from the internet, from your file system, or from the image library provided by Chimera Systems Modeler. So let's change the shape of a missile to the image of a missile. for example, one more, the launch platform. That's it. Now it is much more informative for the people who don't understand SysML. Okay, let's update the index diagram and move to the use cases cell. Use cases can be specified in the use case diagram. Let me create the one directly under the use cases package. Let's name it use cases of missile in mission. As you can remember, use cases should be grouped by system context. That's why we need to represent the missile in mission system context here on the use cases diagram. I'm dragging it here. And I'm enlarging it because all the use cases will be created within the block shape. I also need to represent in the use case diagram the launch platform because it is the actor of the missile in mission use cases, and I can display it as an image. Now let me create the use case. Let it be perform mission. This use case represents one of the high-level goals of a system of interest. Every use case must have a scenario, so-called use case scenario, and it can be specified in the model in the form of the activity or a sequence diagram. Now I'm creating the activity diagram directly from the smart manipulator of a perform mission use case. The diagram is created, and once I get back to the use case using the navigation, I can see that my use case is now decorated with a rake icon, which indicates that my use case has some internal behavior specified somewhere in the model. After I double-click the use case, I get back to my newly created activity diagram. Before starting to specify the scenario, I need to create swim lanes to represent the participants of a related system context. As you can see, the modeling tool allows me to select what participants of a related system context I want to represent as swim lanes. I'm leaving only the launch platform and the missile selected because I want only them to be represented as swim lanes in this use case scenario. And now let me specify a very simple scenario, starting from the initial node. Prepare for launching. Initialize. Launch missile. Missile. Fly to target. Destroy target. Destroy target and activity final. Now let's make our diagram more sophisticated. But for this, we need first of all to analyze the missile in mission system context. As you can see from the launch platform, So to the missile, the mission data are provided. We need to specify the same information in the use case scenario model. For this, I need to refactor this control flow between the action performed by the launch platform and the action performed by the missile to the object flow. And here I need to find the mission data. The next thing to do is to realize all item flows on that object flow. So now the information is synchronized with the system context diagram. But that's not all. As you can see, the missile gets even more inputs from the outside, like coordinates, like weather conditions, like target data, terrain information. So we need to specify the same information in the scenario as well. Due to the limited time, we are not going to do everything, just the coordinates. Okay, let's get back to the activity diagram and let's create the activity parameter node. The activity parameter node type should be coordinates. And now we need to create the object flow to the fly to target action. In order to specify that then the missile performs the fly to target action, it gets the mission data and the coordinates. I want to update the index diagram. First of all, let's drag the use cases diagram and then perform mission activity. As I'm skipping to capture measurements of effectiveness, I can say that we are done with the problem domain analysis from the black box perspective. Analysis from the white box perspective starts from decomposing those functions captured in the use case scenario that are performed by the system of interest, this time by the missile. So if I go to perform a mission use case scenario, I can say that I should decompose the initialize, fly to target, and destroy target functions. However, due to the limited time, I am able to decompose just one, fly to target. For this, I need to create the new activity diagram. Let me do this. The new diagram is created, and as you may see, it already has two activity parameter nodes, which correspond the input pins of the decomposed action fly to target. Just before starting to specify the scenario, I need to change the storage location of this diagram in my model, because currently it is stored in the black box perspective, and I need to move it to the white box perspective, because we are already performing the white box analysis. Okay, let me select the entire activity and let me move everything to the functional analysis package. Now I am ready to specify the very simple scenario of a fly to target function. Let the first function be compute navigation instructions. The next function can be process navigation instructions. Now I need a fork to split the flow. And I will create three more functions. One, make missile fly at required speed. the other make missile fly at required distance from ground. And one more function, make the missile fly to required direction. Make missile fly to required direction. If there is a fork, there should be a join. Let me create one in order to join all the flows into one before finishing the scenario activity final. And I also need to connect the activity parameter nodes to one of the actions. Yeah. So I am done with the white box scenario. And this means that I am already ready to specify the logical subsystems, also known as functional blocks of a missile, because the white box functions helps me to identify them. But this is the task of the next cell. So I need to move to the logical subsystems communication cell. But before doing this, I want to update the index diagram. Here it is. Logical subsystems can be captured using a block definition diagram or just BDD. Let me create one directly under the logical architecture package. BDD missile logical architecture. As I have already captured the system of interest in my model, when specifying the system context, as you may remember, I don't need to recreate it. I just need to find it in the model and display on the newly created diagram. For this, I'm doing this. Missile. And the missile is selected for me in the model browser. So I can drag it to my block definition diagram. And besides, I need to relocate it to move it from the packages of a black box analysis to the packages of the white box analysis, like this. Now, let me specify the logical subsystems, also known as functional blocks. As white box scenario reveals, these are guidance subsystem, flight control system, control subsystem, propulsion subsystem, and structure. Let me apply a quick layout. The next task is to specify how these logical subsystems communicate and what data they exchange. Communication requires to specify interfaces. To save some time, I have created the interfaces for communication with the outside in advance. They are here and I can display them on the diagram. One of the interfaces, the iGPS, is for getting the coordinates, and the other interface, the iMission data, is for getting the mission data. To be more specific, they are the target location and the pre-planned route. Now let me create just one more interface. this time for the internal communication between the guidance and the flight control subsystem, which enables to send the navigation instructions. So let me name it I guidance to follow the same naming convention. I just need to create only one flow property with direction out, because this interface is created from the point of view of a guidance logical subsystem. It sends the navigation instructions out. So nav, and what is important here is the flow property type. Instructions. The interface block is created. Now I need to arrange my model to move the interface block to the proper package interfaces, and to move the flow property type to the exchange items package. In order to assign the interfaces to the system logical architecture blocks, I need to create proxy ports. And for this, let me make more space for the missile block in the diagram. So I want to create a proxy port for the missile for accepting coordinates, and the other proxy port to accept mission data. And the other proxy port must be created for the guidance logical subsystem to be able to send out the navigation instructions. Now I will create a new IBD to specify the communications of a missile system of interest. IBD, and here I need to select to display all the part properties and all the proxy port. As you may remember, the frame of the IBD represents the boundary of the enclosing block. This time it is the system of interest, the missile. So what is inside the diagram is inside my system of interest. So first of all, let me specify the communications of logical subsystems of a missile with the outside. Let's say that the guidance system gets the GPS coordinates and mission date in order to compute navigation instructions for the flight control system. We also need to specify the item flows, coordinates, and also pre-planned route and target location. And now what is left to do is to specify the internal communication between the two logical subsystems of the missile. I am doing this right now. And I need to say that navigation instructions are flowing from the guidance to the flight control. So the rest of communication can be specified the same way. But in order to save time, I'm not going to model the rest. What is left to do is to add this diagram to the index diagram here and get back to the fly to target to create swim lanes and synchronize item flows. So I'm creating here the swim lanes to represent the logical subsystems of a missile. Actually, I need 4 of them and one more. First of all, let it be the guidance. The next one, flight control, propulsion, and structure. Let me enlarge them, and now I can allocate functions to logical architecture of a system. This goes to the guidance logical subsystem. This goes to the flight control system. This can also go to the flight control system. This one goes to the structure. This one also to the structure. And this to the propulsion. Hmm. Here, and finally the activity final. The next thing to do is to synchronize the item flows from the IBD. This time I will synchronize only navigation instructions, because I don't have more. So for this I am converting the control flow to the object flow. I'm setting the navigation instructions as type for pins. I can simply get rid of types showing on the diagram. And here I will realize all item flows between those two logical subsystems. So far, it is only navigation instructions, so they are displayed here on this object flow. So this is the end of a functional analysis. The last task of the problem domain analysis is to establish traceability relationships between stakeholder needs and SysML elements that refine them. These are actually stakeholder requirements, only captured not in textual form, but in the SysML model. The purpose of establishing traceability relationships is to see if all stakeholder needs are considered in the problem domain analysis model. To establish these relationships, I need to create a refine requirements matrix directly under the traceability package. Refine requirements matrix. To create that, to be able to select the diagram, I need to switch to the expert mode and let it be named white box to stakeholder needs. Now let me quickly specify the criteria. Stakeholder needs as column scope, white box as row scope, and the element types for row. The matrix is created, and I am ready to establish traceability relationships. It is very easy. You only need to double-click that cell at the intersection of the relevant stakeholder need and SysML element, like you see me doing now. Self-guided, guidance, logical subsystem, compute navigation instructions, location, also compute navigation instructions, and so on and so forth. For demonstration purposes, it's enough, but then in the real world cases, you may finish the problem domain analysis only then your matrix displays that each stakeholder need is refined by at least one SysML element. Only then you can consider your problem domain analysis completed. And now I can add this matrix to the index diagram, actually to the stakeholder needs cell. That's all what I wanted to show you today. Thank you for your participation and attention.